Today we're going to look at dividing radicals. Before we get started on that, we're actually going to introduce one more form of convenient multiplication, and to do that we need to introduce a little bit of new vocabulary. So the word we're introducing is the conjugate. The conjugate of a binomial is another binomial where you have the same terms, but the opposite sign in between them. So if one of our binomials is a plus b, the other one is a minus b, and vice versa. The reason we find this really convenient is if you multiply them together. A plus b times a minus b is going to be equal to a squared minus b squared, a difference of squares. We've already kind of been using that. Because of this, if we apply the conjugate to something with square roots, when we do that squaring, we're actually going to result in a rational number. And this allows us to not have a radical, for example, in the denominator if we don't want one there. So let's take a look at how this would work if we want to multiply something by its conjugate. The conjugate of 7 root 3 minus 2 root 5 will be 7 root 3 plus 2 root 5. So the same a and b term, but the opposite sign in the middle. If we want to multiply them together, let's write out a multiplication statement. 7 root 3 minus 2 root 5 times 7 root 3 plus 2 root 5. And we now apply the distributive property to multiply these out. I'm going to do that with the box method. And I'm going to try and make my box big enough that I can get all these terms in there. So we'll do 7 root 3 minus 2 root 5 going across the top, and 7 root 3 plus 2 root 5. And then we'll multiply box by box. The first box I'll highlight temporarily has 7 root 3 times 7 root 3. What I'm going to do is multiply the coefficients first, and then the radicals afterwards. So the coefficients 7 times 7 give us 49. And then root 3 times root 3 gives us just 3. So that will be 49 times 3, whatever that's equal to. Similarly for the next box, negative 2 times 7 is negative 14. And then root 3 times root 5 is root 15. Next row, same thing. We have positive 14 root 15. And then positive 2 times negative 2, negative 4, and then root 5 times root 5 will be 5, so this will be negative 4 times 5. If we want to bring this out and write it out, I'm going to point out that our two middle terms are like radicals that we can combine, but also notice the coefficients for those. We have a negative 14 and a positive 14. Those two terms will zero out. So this is equal to 49 times 3, which is 147. And then negative 4 times 5, so minus 20. This is equal to 127. Now you'll notice that this term here was actually a squared. And this term here was actually b squared with a minus sign in front. So this is a squared minus b squared. We're essentially doing a difference of squares. Multiplying it out with the difference of squares saves you from having to do the box and then have those two terms that end up canceling out anyways. This is going to come in really handy in just a little bit, so we will come back to it. Let's do a quick refresher of how to divide a radical. So to divide a radical, we're going to look at our coefficients. It says divide coefficients. This is where I like to remind you that you can also reduce fractions. So I'll say reduce fractions to. Divide your radicands, assuming they have the same index, and then simplify your remaining term. So you'll notice that here, if we are dividing x and y as our coefficients, we can divide those separately. And then if we have the nth root of a and the nth root of b, we can combine those into a single a over b as long as we have the same index n. We're going to take a look at a couple examples of that. We're also going to assume that if we are taking an even root like a square root, our variables a and b must be greater than or equal to 0, just so we're not taking a square root of a negative number. All right, so we come back to our general word simplify, which means do all of the operations we see, and then write your answer in simplest radical form. For the first one, we've already done something like this. We're going to take the square root of 30 divided by 6, and we're just going to evaluate the radicand. 30 divided by 6 is 5, so this is just equal to the square root of 5. The second one doesn't divide quite as straightforward, but we can reduce that fraction. So if we have the fraction 18 over 75, that is equivalent to the fraction 6 over 25 when we reduce it. Now, this is as far as you can reduce the fraction, but this is not considered fully simplified because we have a fraction in a radical sign, or if we split it up, we're going to be taking the square root of the denominator. So we do have a little bit of an extra step here. Just to make it really clear, what I'll do with this one is I will break it up into the square root of 6 over the square root of 25. Now we no longer have a fraction in a radical, but we are dividing by a square root. Luckily, the square root of 25 is just 5, so this is root 6 divided by 5, or root 6 over 5. You may occasionally see like a fractional coefficient like 1 over 5 times root 6. That would also be equivalent. I would probably prefer this most of the time. Now that one worked out really nicely because we had a radical in the denominator and we were able to evaluate it. Let's look at what happens if you can't do that. So in this case, when the denominator of a fraction is an irrational number, the denominator is non-terminating and non-repeating. It means you can't write it as a fraction. As a decimal, the decimal keeps going and does not repeat the same pattern. That makes it difficult, and we say it's impossible to divide by a number like that. So we do not like to have a denominator where the denominator is irrational. What this basically means for us is if you see a square root in the denominator like this, you must rewrite whatever term you have so that you do not have a square root in the denominator, but it should still be equivalent. The process of doing this is called rationalizing the denominator, which is basically making sure that the denominator is a rational number. Now, the easiest way to deal with this is to multiply by 1, but we're going to do so in kind of a smart way. So for example, in this example here, root 5 divided by root 7, we don't want to have a square root in the denominator, but we do know if we were to multiply by the square root of 7, the square root of 7 times the square root of 7 is equal to 7. We also know that any number over itself is going to be equal to 1. So we kind of pick a smart radical to multiply by in the numerator and the denominator, knowing that we're actually just multiplying by 1. Our new numerator is root 35. And our denominator is root 7 times root 7, which is just 7. If that feels a little weird, think about root 7 times root 7 as being equal to root 49, and root 49 is equal to 7. I'll just pop that in brackets. All right, let's do something similar for the next one. Now for the next one, we have a couple of options. The first option is you can just go ahead and multiply by root 20 over root 20. The second option is you can notice that you can actually simplify the denominator a little bit, and that's kind of the option I want to go with. So we have 15 over root 20. Root 20 is broken into the square root of 4 times the square root of 5, so this is actually 2 root 5. It's okay to have a 2 in the denominator, we just don't want to have a root 5 in the denominator. So what I'm going to do is multiply times root 5 over root 5. And rewriting together, that would be 15 root 5 over 2 times 5, which is 10, but I'll do it in 2 steps. Now our denominator is rationalized, but we do have 15 over 10, which can be reduced. So we divide out a 5 from our coefficient or our number, not the radical. So this is a 3, this is a 2, and our fully simplified version would be 3 root 5 over 2. Notice when I did that division, I only did it once in the numerator and once in the denominator because I only have one term in the numerator. There's multiplication happening. So that 15 root 5 is one term that I divided by 5. Similarly, in the denominator, it's only one term that I divided by 5. And that's the basic idea for rationalizing. So we rewrite so we don't have a radical in the denominator. It's very straightforward when we only have one term. If we have more than one term, that's where we need to take advantage of the conjugate instead. So let's take a look at the next example. Now for this example, I'm just going to point out, and this is not correct, but I'm just going to point out, if we wanted to multiply by root 5 over root 5, what would happen? We would have a 6 root 5 in the numerator. What happens in the denominator? Well, we have two terms that are each going to get multiplied by root 5. And we would end up with root 5 plus 5. Is it equivalent? Yes. Is it simplified? No, because there's also a square root. So just multiplying by the square root of 5 is not enough to rationalize the denominator. I'm just going to take that away. But this is where we can take advantage of the conjugate. So the conjugate is going to give us a way to multiply the denominator so that we do not have any radicals. As a little reminder, we think of this as a plus b times a minus b, and we know when we multiply that out, it will be a squared minus b squared, no square roots anywhere. So let's multiply. We're going to multiply by the same thing in both the numerator and denominator. It will be 1 minus root 5, the same terms for a and b, but the opposite sign. The other thing you want to keep in mind is think of this as having an implied bracket around it. You need to multiply the entire numerator and the entire denominator. Let's write this out with some brackets just so you can picture that. It's 6 times bracket 1 minus root 5 over 1 plus root 5 times 1 minus root 5. Our numerator, we're just going to expand out, so this will be 6 minus 6 root 5. And our denominator, we're going to take advantage of the fact that this is a squared minus b squared. So this is going to be 1 squared minus the square root of 5 squared. Numerator stays the same, 6 minus 6 root 5. The denominator is 1 minus 5. The kind of key thing to notice there is that the square root of 5 being squared is just equal to 5. So we have 1 minus 5. We can still simplify this a little more, so let's keep going. Numerator stays the same, 6 minus 6 root 5, but this is over negative 4. Now I can't directly divide by negative 4, but I can divide by 2. And I need to do that from every single term. How many terms are in the numerator? Yes, that's right. There are two terms being separated by a minus sign. So each of the two terms needs to be divided by 2. This becomes a 3. This becomes a 3 root 5. In the denominator, negative 2. So we rewrite this as 3 minus 3 root 5 over negative 2. It would be fine to leave it like that. I'm going to call this one okay. It is pretty much simplified. The only thing you notice there is we have a negative sign in the denominator. There's nothing wrong with that, but you won't notice a lot of answers formatted in that way. One of two things will happen. The first one is that we will put the negative sign in front and then have 3 minus 3 root 5 over positive 2. Or we may distribute that negative sign into the numerator and change the signs in the numerator to have negative 3 plus 3 root 5 over positive 2. And both of those are more likely to be something you will see. The last thing I'd like to point out for this is be very precise in where you put your negative sign. A negative sign in front of the 3 is just for the 3. A negative sign in front of the entire term, like we have here, is for the entire fraction there. Now let's go ahead and try a couple of examples for you. So out of these exercises, you should be able to do A and B fine on your own. You're welcome to try C if you're feeling adventurous. You can pause the video and try the first two, and then come back and we'll go through them together. All right, starting with A. For A, we want to look specifically at the denominator when we decide what do we want to multiply by. We can also check our coefficients, but 5 over 2 isn't really going to reduce. So we'll just look at that root 11 in the denominator and multiply by the square root of 11 over the square root of 11. That way we're not changing its value, we're only multiplying by 1. In the numerator, we now have 5 root 66. And in the denominator, we have 2 times 11, which is 22. This is where I would check, can we simplify the radical in the numerator? Can we simplify the 5 over 22? And I think the answer to both of those questions is no, so we're actually done. Not too bad. All right, let's take a look at B. For B, I am noticing that lovely root 90 in the denominator, and I'm thinking to myself, we should really simplify that first. So let's just rewrite this with that one radical simplified. We have 5 root 7 over 2 times, let's wrap that in a bracket. We can factor 90 into 9 times 10, so this will be 3 root 10, and then close the bracket. Let's extend that a little bit. Okay, we can multiply the 2 times 3 and have a 6 root 10, so let's just do that. 5 root 7 over 6 root 10. And now we don't want to have a root 10 in the denominator. We multiply by root 10 over root 10. As a quick note, if you didn't do that simplifying, you could just multiply by root 90 over root 90. You would have to do a lot of simplifying afterwards to deal with that, but you could do it. All right, our numerator. 5 root 70 over our denominator is now 6 times 10, or 60. Sorry, that's a times. Let's clean that up a little, since we're making a big deal about precision. There we go. And then we look at, is there anything we can reduce? I am noticing that 5 and 10, so why don't we do that right now? This will become a 1, this will become a 2. Notice we only have one term in the numerator, so we are only dividing out of the one term for each. That leaves us with root 70 over 6 times 2, 12. Root 70 over 12. The last thing I would probably also check is the square root of 70, but if we go through the factors of that, it's just going to be 2 times 35, so 2 times 5 times 7, no perfect square factors. So this is fully simplified. Okay, well, hopefully those two felt okay. Let's take a look at C, because C is a little more fun. And the reason it's a little more fun is that lovely index right there. Notice we have a cube root. Oops, sorry. Let's bring that back. There we go. Sorry about that. So notice that we have the cube root in the denominator. If we try to just use the same technique we were using before and multiply by the cube root of 4 over the cube root of 4, is that going to rationalize the denominator? Let's just line that up a little. Think about the cube root of 4 times the cube root of 4. Is that going to be enough to rationalize your denominator? The cube root of 4 times the cube root of 4 is not actually equal to 4 yet. If you think about it with fractions, this is 4. It's being cube rooted, so it's to the power of 1/3, right? If you multiply it by another 4 to the power of 1/3, that would only be 4 to the power of 2/3. You need to do it again. That would be 4 to the power of 3/3, or 4 to the power of 1. when you add those exponents. So we actually need to do this twice to rationalize our denominator because it's a cube root. If it had been a fourth root, you would need to do it 3 times. That way you have a total of 4 of them. We have a cube root, so 3 of these cube roots multiplied together will be equal to 4 in the denominator. And we need to multiply them in the numerator as well. So in the numerator, we have 5. And then we have the cube root of 4 times the cube root of 4. That's being multiplied by itself. You can think of it as being squared, or you can multiply the 4s. Let's multiply the 4s. So the cube root of 16. And this is now over 4. That's kind of the big step in rationalizing the denominator. And as a last step, let's check if there's a way we can simplify the radical in the numerator. So the cube root of 16 is the cube root of 8 times 2. And we know that the cube root of 8 is going to be 2. Let's just bring this over to the right. This is going to be 5 times 2 times the cube root of 2 over 4. And now look at that. We have something else we can reduce out. So 5 times 2 is 10, but we also have the 2 and the 4. That becomes a 1. That becomes a 2. And this is actually going to be 5 times the cube root of 2 all over 2. Notice this one actually has a lot of steps. So aside from rationalizing and knowing that we need to multiply by that cube root twice, so we've got 3 of the 4 terms, we also have to simplify the radical in the numerator and then simplify the coefficients afterwards. A lot of steps. All right, the last kind of problem we're going to look at is using some distributive property when we have, again, that need for a conjugate. So noticing that we have multiple radicals in the denominator, we still have 2 terms or a binomial, so we can still multiply by the conjugate. It's going to be a nice long one. This is going to be 2 root 3 minus 3 root 2. And the same thing in the numerator. That way we're just multiplying by 1. Okay. As a gentle reminder, even though you don't see the brackets there, there is an implied bracket there, 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 and there. The numerator will need to be multiplied out the long way. The denominator will be a difference of squares. So for the numerator, I'm not going to do a box, but I am going to do the little lines to show what I'm connecting. We're going to do 2 root 3 times 2 root 3. That's going to be 2 times 2 is 4, and then root 3 times root 3 is 3. So 4 times 3. Then we do 2 root 3 times minus 3 root 2. So minus 6 root 6. Then we'll do negative 3 root 2 times 2 root 3. So minus 6 root 6. And negative 3 root 2 times negative 3 root 2 plus 9 times 2. All of that is just the numerator. In our denominator, we have the difference of squares. So our a term is 2 root 3. I'll put it in brackets. 2 root 3 squared minus our b term, also in brackets, 3 root 2 squared. This is a lot of little pieces, so let's kind of try and take them step by step. 4 times 3. Let's go 12. And then we have another term here that's going to be a number. So let's write them in that order. 12 plus 18. And then we have minus 6 root 6 and minus 6 root 6, like radical terms. Those ones are going to become minus 12 root 6. In the denominator, 2 times the cube root of 3, all being squared. 2 squared is 4. The square root of 3 squared is 3. So this is 4 times 3 minus 3 squared is 9 times the square root of 2 squared is 2. So we have 12 minus 18 in the denominator. So in the numerator, let's combine 12 plus 18 is 30. This is 30 minus 12 root 6. In the denominator, we have negative 6. As a last step, we notice that we have a lot of multiples of 6, so we can divide by 6 here, here, and here. We could have probably also divided by -6. That might have been nicer, but let's do 5 minus 2 root 6 over -1. This is where I would say the answer is okay, but let's take it a step further. Either put the negative sign in front of the entire fraction, or just divide by -1 and make this -5 plus 2 root 6, and you'll notice that's the preferred answer in the answer key as well. Okay. This one right here is a really good example of the level of simplifying you need to be able to do. So you need to be able to multiply by the conjugate when you have multiple radicals in the denominator. You need to be able to combine any like terms and then also reduce your fraction and your radical as much as possible. All right, and that's it for today.